So for this problem right here, I would think that option A is the correct answer, where it says that there is a local maximum of f prime at x equals c, that would mean that we have a point of inflection. I'll explain why. Think of just a graph here. Let's say this is the graph of f prime, okay, the derivative. Now they're saying there is a local maximum for this function. Let's say here, let's pretend that is our local maximum. So this is the derivative graph, not f double. This is f prime. But consider the tangents. Let's say that we have a tangent here, and then we have a tangent there. So what is this saying? Since this is a local maximum, that means that it is above the points that are to the left and to the right of it, which means that the graph goes up and the graph goes down. That's a local max, which means on one side, you have something that's increasing, and on the other side, you have something that's decreasing. That just goes with the nature of being a local maximum. Now, how does that relate to the second derivative? Well, recall that tangents reveal the sign of the derivative of the graph that you are looking at. So, since this graph is f prime, when we look at these tangent lines, their sign describes the second derivative. So if that's x equals c, so let's say that we have a number line that represents f double prime, whether or not the second derivative is positive or negative. I claim that the second derivative before c has to be positive. And I know that because before c here, the graph is going up. And I claim that the second derivative from c after has to be negative. Maybe not forever, but I'm just talking about this general vicinity, just this general area surrounding this local maximum. I don't know what happens way out left and right. I'm just focused on this section here. And in that section, f double prime has to be positive, negative, because the previous function, the first derivative, goes from increase to decrease. And since we have a second derivative changing sign from positive to negative at c, then yeah, in that case, we'd have a point of inflection here. Now for this one here, they're saying that f double prime of c equals 0, that implies that c comma f of c is a point of inflection. But that is false. And you only need one counterexample to prove them false, or to prove it that this is not true. And consider this example, f of x equals x. This is the graph of f of x equals x. What is the derivative? The derivative is 1. And what is the second derivative? The constant function 0. So, because here, it doesn't matter what you plug in for x, all these points, you can pick any one of these points. I don't care which one you pick. There's lots of points on this line. Regardless of which one you pick, if you plug in x into the second derivative, it's just going to mean 0. Does that mean that the point that you use is a point of inflection? No. That's what this is saying, and that's why this is a lie. You can see here, this has no point of inflection ever. So this is called a counterexample. It's a very basic, trivial counterexample, but it goes to show that this in and of itself is not enough evidence to say that this is our point of inflection. We need this and a few other conditions. But as is, that's not enough. False counterexample.